But Europe is having a really nice competitive edge in terms of the research on the Perovskite side. And therefore, now there is a lot of ongoing endeavors to basically combine this research in collaboration with industry to bring products eventually onto the market.
The other technology we're well known for is the PERC technology. The patents on that had all expired by the time the industry got around to using it, which I think was one of the reasons that the industry adopted it so broadly and quickly.
What we developed can be used in the future by, for example, an industry company. It's not published yet, but that it might be an open source corridor that we can be transferred to industry.
The clean energy industry is always defined by technology. Falling costs, cheaper processes, higher performance, more durability. These are the principles that really underpin solar energy, battery energy storage, electrification. And that's why it's so important to have the R&D community, research institutes, and these people that are carrying out fundamental research as a part of the discussion. And my guests on the podcast today were Martin Green from the UNSW, the University of New South Wales, really one of the leading solar energy researchers and solar cell researchers over the last 40 or 50 years, and the inventor of the PERC cell, sometimes called the father of modern photovoltaics. Martin was joined by Nina Munsker. She's a team leader, stationary energy storage systems at the Karlsruhe Institute of Technology, and Nina gave us the perspective of energy storage and their integration into energy systems. And then a young researcher joined us in the conversation as well, Ivona Kafedjiska from the Helmholtz-Zentrum Berlin, and she gave us an update on the HZB's activities when it comes to Perovskite solar cells, which are proving particularly promising and becoming commercial much faster than many people had expected. One of the key takeaways, I believe, from this discussion is about the powerful nature of open flows of information, open ideas, and the sharing of technology and takeaways that can come from publicly funded research institutes and universities like the PERC cell, for example, that Martin Green sketched many years ago and quickly became the mainstream technology in the PV industry, changing the energy transition and accelerating the uptake of PV right around the world. My name's Jonathan Gifford. This is a special edition of the Smartery podcast. Martin Green from the UNSW, Nina Munsker from KIT, and Ivona Kafedjiska from the Helmholtz-Zentrum Berlin. Thank you very much, all of you, for joining, powering through the resilience of renewables, the Smartery 2025 podcast here in Munich. It's great to have members of the research community with us today because we're exploring the theme of renewable energy resilience. And of course, much of the outstanding progress that's been made in renewable energy and energy storage over the past decade, 20 years or more, has really been underpinned by technological progress. And I think that's an important theme: better efficiency, more performance, lower cost. And it doesn't happen without the research institutes, the universities making these gains. Martin, it's wonderful to have you here in Munich, a solar luminary from the research community. Can you just tell me, when you were carrying out some of this kind of really fundamental solar research, technologies that became mainstream relatively recently, like PERC technology, how important was the public funding that you and your team were able to attract to make that progress?
Yes, I think the industry's relied very heavily on public funding to get where it has got to, which is, like now the major source of new electricity generation worldwide. But public funding was certainly very important in our development. And, I guess I started during the programs in the US, which really kick-started the industry. That was the Project Independence that Nixon started, and massive funding in going into solar over that era, and a lot of competition between different groups. And that was an important part of too, the competition between groups. Internationally, Japan followed the US in starting its own Sunshine Project, and Australia followed as well. And that helped us get funding, and we were competing against our colleagues in the US. who are always also receiving large amounts of public funding under the large flat plate solar array project that is being managed by JPL. We also managed to tap into some US public funding because we started setting our world records in 1983. And because we had been identified as having unique capabilities, we were able to get US funding, which was very difficult to get, of course. And that really lifted our activities quite substantially.
Well, you mentioned competition, because I think some people can think public funding, particularly if they come from industry or finance, and they think, this is just ongoing assured funding, or this is kind of easy to get. It's not competitive like in the free market. It's highly competitive, though, you mentioned in the early days. So how important is it in terms of this competition for public funds, and how it drives innovation and motivates teams and helps achieve progress?
Yeah, no, very important in our case. And the good thing about solar is that there's well-established procedures for measuring the efficiency of a cell. And in the US program I mentioned, the subcontractors under that program had to have their results certified if they were going to talk about, a brand new result that they'd got that was much better than had been obtained before. So once we started setting world records, we worked hard to make sure that that procedure continued. And it's become established in the field now that if you claim an efficiency record, it's not regarded seriously unless you have the result independently confirmed. And that's really helpful to us because we were competing for the top Australian funding schemes, like 10 centres of excellence awarded around the whole country across all fields, including medicine and so on. And because we were able to show that we were doing better than anyone else in the world, it made it possible for us to be viable contenders in that type of, large-scale funding locally. So, so we benefited enormously from the public funding, and the nature of the technology has helped us greatly at being so quantifiable. You can't just spin a good story. You've got to be able to deliver real results.
And it has to be verified by a third party, which is now an established process.
Yes.
Now, turning to kind of emerging or new areas for research, Ivona, I'd like to bring you into the conversation. At the HZB, another leading solar research institute alongside the UNSW, what are some of the areas where there's fundamental research going on that are looking really encouraging for solar PV technology?
Well, first of all, thank you for the invitation. I'm very happy to be here. So actually, there is fundamental research in various fields in the PV sector. One thing I also want to point out before I discuss a little bit more in details what we are investigating is that research in PV is always there, and is really the aspect that made the whole difference in why we see PV on such a large scale and so much of our rollout and interest in the public community is because we were able to bring this research directly into the industry, improve the efficiency and decrease the cost of the solar modules. Nowadays, when we are looking into research, I would say we can largely group it into 4 large groups. The first one is advancement of efficiency and technologies of existing or novel and upcoming PV technologies. So for example, this could be improvements in the typical silicon solar cells that we are using, or upcoming technologies such as Perovskites or silicon perovskite tandems. Another aspect that we are seeing that is becoming largely popular in the research community is the whole aspect of sustainability and recycling. And this also comes from the idea that we now have, on a European level, the Critical Raw Materials Act, which basically postulates that there are certain critical raw materials that go into PV that we are kind of limited in using. So it would be very good if we have ways to either reduce their usage, fully substitute them, or find a way to recycle them and then reuse them again and again in modules. And especially the recycling and reusage is still an ongoing research, and a lot of research groups are looking into this. Then we are also having, as a third pillar, I would say, a novel PV concepts or novel PV integration. So up to now, a lot of people, when they think about PV, they simply think about modules installed on roofs. But nowadays, what we are slowly seeing is that we also have development, for example, on vehicle integrated photovoltaics, building integrated photovoltaics, and novel concepts, even like agri-photovoltaics and floating photovoltaics, both of which can substantially also help, like, let's say, for example, working between photovoltaics and agriculture in fields that are currently maybe having problems because of climate change and it's a very dry area. And the last concept that I also like to mention, and maybe the colleague from KIT can connect here a little bit, is any kind of hybrid systems where PV plays together with any kind of storage or new types of renewables. So for other types of renewables, like wind, for example, but also things like smart grids, digitalization of PV, integration of automated and AI-assisted PV systems, and so on. That's also all part in the research community, as this is also something that needs to be further developed and tested.
Yeah, so it's a very broad
Very
field
broad, indeed.
of search.
I just wanted to underline, to point out that there is still a lot to do, and research can play a really big role.
Yeah, great perspective. And of course, you know, in the early days of solar cell research, Martin, when you were involved, it was about making solar viable on land. That was one of the great goals, to make solar cheap enough that it makes sense to install down here on Earth. Now, looking forward, one of the key enablers of solar will be energy storage, of course, to soak up some of that solar generation and make it available in the evenings when we can use it. The KIT, Nina Munska, is deeply involved in energy storage research. What areas of energy storage do you find most exciting or promising, from the research institute perspective?
Interesting question. So my research is more in the integration part, which was just mentioned, but I think one other perspective where there's a lot of research going on is still in new materials. So like also on sodium-ion batteries, or also regarding cycling, so that the materials are more easy, or the batteries are more easy for recycling and to be reused. And then like the area-wise, it's mainly the integration part. So how can they be better integrated into the grid? How they can be used more effectively to also support the grid? How can battery storage be integrated with PV, but also with the other sector coupling like EV charging, with the heat pumps, for example, with all the heat sector. And there's a lot of research on intelligence going on. And maybe one aspect which you also goes in that direction is like a lot of AI, artificial intelligence, where you have some predictive maintenance and stuff going on in research, I think.
And I understand the KIT actually has a project that was a finalist here at the Smartery Outstanding Projects Award. That was looking at combining different types of energy storage technology, including flow technology, but also combining the provision of energy storage and power, but also heat. So integration across sectors is also an important area for energy storage research as well, or energy system research.
Yes, sure. In the beginning, like 10 years ago when I started, it was mainly how can the storage system be charged and discharged more intelligently. And now it's going further on into the heat sector. How can PV be better integrated? And when do we charge the battery? How that it ages, for example, slower, that it can be used be longer, and things like that.
Okay, well, there's a lot to do, and it's a lot of broad work being done. We touched on public funding and the importance of that right at the start. I want to come back to you, Martin. The UNSW has also played a very important role in the foundation of the Chinese solar industry, Chinese solar cell and module manufacturers, many of whom, or the pioneers, came from the UNSW and were your graduates or even PhD students. How important is this role for universities and research institutes to partner with industry partners, both in terms of applying their research and then also finding ways that this research can be supported?
Yes, yes. So from our point of view, it was all serendipitous. Like we didn't plan to establish an industry in China, although it's been critical to the reduction in costs of photovoltaics that we've seen. Like without the Chinese industry, being so effective in manufacturing the cells, we'd still be in an era where solar was promising but too expensive to exploit. But when my student decided to establish in China, we'd been to China before looking at business opportunities because we knew we had low-cost technology for making high-efficiency cells. And we thought, back in the day, China products were not regarded as being first class, but if they were making the most efficient cells in the world in China, it was a way of adding value to a product that could be produced quite cheaply there. But it was just a hopeless situation. There was no infrastructure there at all. So when my student, Zhengrong Shi, said he wanted to go back to China to set up solar manufacturing, I said, oh, Zhengrong, you know how tough that's going to be. It's crazy. And so I was quite pessimistic about his chances, but we gave him all the help we could in getting established, and some of our more experienced people went with him to set up the first commercial manufacturing line in China. 2002, September, it opened. I think it was 10 megawatts, so it wasn't massive, but that was, the industry then was much smaller than it is now, so it was quite a substantial contributor to the total industry demand. But that was a huge success, and he was able to manufacture a lot less expensively than in Germany and Japan, who were the two leading manufacturing countries in that era. And so he just ploughed all the profits back into increasing his manufacturing and got noticed by some US investment banks. This was, around 2002 type, 2004 type era. And Chinese stocks were very popular in the US. So Morgan Stanley and Goldman Sachs approached him about a management buyout of his original Chinese investors, which he participated in, and suddenly owned a large share of a company he was only a minor shareholder in, and floated on the New York Stock Exchange in 2005. So it was the first private Chinese companies to float on that exchange, and it was the biggest technology float of 2005. So he did really well, and that's what opened the floodgates for investment in manufacturing in China. A lot of people think it was the Chinese government that sponsored it, but they thought solar was always going to be too expensive, so wasn't any point worrying about it, and they put their efforts into building up the wind industry. But there was about $7 billion pumped into the industry from 2005, 2010 by US investors, which established Chinese manufacturing. And I think it's 6 out of the 10 largest manufacturers in China now started from this US investment. So Zhengrong started with $6 million invested by some local companies in China that had their arms twisted by the local government to help him out. But that $7 billion was orders of magnitude larger amounts of money than what the industry could expect to raise before. And that's what really kickstarted the whole manufacturing industry, in that these cashed up companies then had to sell what they were producing, and the only way of doing that was to lower prices, and it caused very competitive industry and, low margin industry, but it's really been very competitive ever since.
And then it also required a generation of Chinese solar engineers. And the UNSW has played a role in training these students, which is kind of a windfall for the university and your ongoing funding for research, because these students came to the UNSW. How important was that relationship in terms of continuing your research and expanding the solar activities at UNSW?
Yeah, it was slightly annoying at the time, actually, because I think it was part of the due diligence of the US investment banks. They had to, the companies they were backing had to show they had contact to, sound technology. And because Zhengrong had done well, we were the logical choice for the source of the good technology. So all my students, mostly those that could speak Mandarin, got very quickly recruited and became CTOs, some of them quite young, of these startup companies, and have done very well, since. The other thing was that the university had started the world's first undergraduate program in photovoltaic engineering in 2000. I think it remains, the only one in the Western world still up to the present day. So we've trained over 2,000 students who have ended with Bachelor of Engineering in photovoltaic engineering. We expanded out to renewable energy engineering as well. And half of those have been, Australian universities very dependent on overseas fee-paying students. So half the students we've put through have been Chinese nationals who have gone back to participate in the industry. So the ones that we graduated that ended up back in China set up a WeChat group. You're only allowed 500 in a WeChat group, so they've started their second WeChat group now. And, in Shanghai and Beijing, they have monthly get-togethers of, former alumni from our group. So, we've had a massive impact upon training people within the industry. And the people that study with us, they automatically get skyrocketed through the organisation that recruits them because they have our credentials.
Well, it's a slightly unique situation, the UNSW in Australia playing that role with the Chinese industry. Looking at Europe, Ivona, of course, here in Germany, there was a very close relationship between the PV production equipment suppliers, many of whom did very brisk business supplying these Chinese manufacturers when they were scaling their operations. How do you see it? How research institutes, equipment suppliers, and potentially manufacturers are operating together in 2025? You mentioned Perovskite technology and tandems. I imagine that's an area where there's quite a lot of activity.
Indeed. Well, all of this need to collaborate together to really make impact, especially on the industry, and to bring products that people eventually can use and benefit from. So we cannot really look any of these sectors as an isolated entity. They just simply have to work into synergy in order that we have a certain high quality product. So on a European level, certainly right now we are looking a lot into industrializing perovskite technology, and specifically tandem-based perovskites, because right now the European industry is in a little bit of a specific situation, in the sense that we have extremely cheap but also high quality products from China that are based on silicon. So therefore it is very difficult to compete or even complement this industry when it has, the capacity that it has. But Europe is having a really nice competitive edge in terms of the research on the perovskite side. And therefore now there is a lot of ongoing endeavors to basically combine this research in collaboration with industry to bring products eventually onto the market. So on a European level, we have collaborations between industry and research institutes, but there are also independent industry working on its own. So for example, we have Oxford PV, which already supplied certain amount of modules to the USA, and these modules are attached to the grid. So we are yet pending to see what will really happen. So they are silicon perovskite-based tandems, and they are full-scale modules. So we are all very excited to see what the first results will be from these modules. But I can speak a little bit more on the research side. So for example, we at the Helmholtz-Zentrum Berlin, we have an ongoing project which is called the Pepperoni Project. And this project focuses on the three main bottlenecks right now for perovskites, or three main challenges. The three challenges that really determine if perovskites will make it on the market or not. And that is basically, the first one is the upscaling. So can we really make big modules in a reliable and reproducible manner? The second and very important aspect is the stability. Can we really guarantee that they will perform in the field as long as or at least close to what the silicon modules are performing. And the third one, I would say, is slightly on a level, little bit less important than the other two, is the whole sustainability and toxicity concept. So as you know, or maybe you might know, a lot of the perovskite has lead in it. So there are, for example, some concerns about the toxicity of the lead. But it's very important to keep in mind that this is enclosed in the module. There is a lot of, lead capturing materials that are into the panel, and also that the amount of lead is so low that actually people will not be getting in touch with this lead when it's a finished module. So therefore, I'm saying this is slightly less important or relevant than the other two. So the Pepperoni project is looking into the upscaling and into the stability, is looking, for example, by developing machines that could actually produce these upscale modules, and in close collaboration with von Ardenne. So they are actually the machine manufacturer that supplied a lot of the machines for our research at HZB. Then we are also having collaboration within this project with Q-Cells, who are also a mature company for PV and for silicon. And we are looking into all aspects. So for example, developing perovskites on top of the silicon from Q-Cells, testing the machines from von Ardenne, looking into all sorts of processes, not only for the development of the perovskite, but also other layers in the cell, and all of this, how does it come together so that eventually we have a finished module. So this is, in short, for example, one really nice example of how industry and research can work together to really develop this technology, and hopefully that it sees the light of day. But there are, of course, many, many other projects and many other research centers, not only in Germany, everywhere around Europe. There is a huge race, I would say, right now, who will really get the first finished reliable, reproducible tandem out there that will actually hit the market and starts making profit.
That is interesting. And also interesting that Oxford PV, I saw recently, signed a deal to license its IP to Trina Solar, so one of the giants in the industry. And I do want to touch on IP, intellectual property, and the prospects for licensing technology from research institutes just a little bit later. But Nino, I would like to bring you back in, talking about grids and integration. It's a huge topic of discussion here in Munich at the Smartery 2025. Of course, we had the event, the blackout in the Iberian Peninsula, which many, many people are talking about. What can you tell me about research programs that are ongoing to ensure kind of resilience of the grid, to ensure that batteries, as you say, operate effectively on the electricity network and build a more resilient European electricity network?
You mean like European project? You mean funding from governments?
European projects, funding from governments.
I think there's one thing is the European funding by the European Union. These are mostly big, large projects. They're difficult to get normally, and then you have the national funding. Where it's often a project what was already mentioned between industry and research partners, where they partner together, and the what is developed can directly be used within the industry.
Mm-hmm. And are there any projects that are particularly promising from your side that, or perhaps you're involved with, that you see has a big potential?
Let's see. I can talk about, for example, for the thing we just handed in for the award. Let's see if it will get great. What you tried there was to couple different storage systems, which will be, if it's not that project, it will definitely be one thing to couple different storage system, different sectors. What we did there, we coupled a vanadium redox flow battery together with a lithium-ion battery to get most of it of both technologies, and together with also the heat sector, so with warm water heating. And we tried to use we used the redox flow battery as a heat and electricity storage to make it cheaper, because at the moment it's mainly lithium ion, which is much cheaper, obviously, and the efficiency is much higher. But in that way, we can lose the waste heat. And by using the waste heat, the efficiency of the redox flow battery gets much higher. So when we calculate it more or less, it should be, if costs can be reduced, it should be compatible within, like 9 years, like the amortization period. So even that, if that might not be the project or technology which will take place, but it's kind of these projects where you have interaction between different sectors, which are definitely important.
Yeah, and then combining storage technologies, but also heat and power is a huge area and a difficult subject for to really make progress in the economy. We hear it a lot from politicians, but actual projects are more difficult.
It's difficult, and I have the feeling that at the moment, every company works on their own type of energy management. And so there's not a general platform. That's why we, for example, used the OpenEMS to get in a more general way that what we developed can be used in the future by, for example, an industry company. That it's directly, or it's not published yet, but that it might be an open source corridor that can be transferred to industry.
Really interesting. So for energy storage, open source software could be a really interesting tool from the research community to enable more deployment.
I think this is when we talk about Helmholtz research, this is also one thing which they are trying to push, is open data, open source, open platforms, that it's not somewhere just written in, that it's not written in some paper somewhere, nobody can find it, that it's open source and can be used further.
Yeah, that is promising. And the other side of that is kind of intellectual property, and we've seen, we have seen a kind of activity in that space in the solar industry in particular accelerate in the last couple of years. Martin, I know that at UNSW you had some success in terms of licensing technology that was developed in-house in your R&D teams. What can you tell me about that in terms of how effective it was?
Yeah, so I've got sort of a bit of a mixed attitude to IP. So, initially when I'm a young researcher, I thought, well, I don't want to make any money from any results of my research. I won't worry about patenting anything. But when we started talking to companies and trying to get them involved in our research, we realized we had to have patents for them to take it seriously. So sort of changed my attitude to it. So, we licensed one of our technologies to BP Solar, and they used it we licensed them in 85, and they used it up to 2006, so when they dropped out of manufacturing. That was their Saturn product. And that's been our biggest commercial licensing success. But the other technology we're well known for is the PERC technology. That's just an acronym for the type of cell. Won't have time to go into details about it, but the patents on that had all expired by the time the industry got around to using it, which I think was one of the reasons that the industry adopted it so broadly and quickly, and there weren't any intellectual property barriers in relation to it. The industry is now using TOPCon, and we made our first TOPCon. So, that was the one that I didn't patent back in, I think it was 1972, when we showed that you could get high voltage from these tunneling types of structures. But that's where all the litigation's over. And it's actually a bit of a shame, I think, because, some of the companies claim to have like hundreds or even thousands of patents on TOPCon. So, hey, you can have hundreds or thousands of, bewildering, innovative concepts that have gone into your TOPCon cell, I'm not sure. But, a lot of the patents are just method type patents, and, kind of add ingredient X and you get a slightly better result sort of stuff. So it's all fairly trivial, the amount of the patents that are going in now, and the sheer quantity of them is just bewildering. There's thousands going in a year on basically the same technology. So it's a bit of a shame for the industry, I think, that it's wasting its time in battling there. I think one of the strengths and why the photovoltaic industry has done so well is everyone's gone for a uniform technology, which has allowed the material suppliers to focus on getting the cost out of the material everyone wants, and the equipment suppliers on making gear that everyone's going to buy. So Australian Cadell Evans won the Tour de France once. And in that era, I used to talk a lot about the peloton and pack in terms of the solar industry. Like, you're going to get a breakaway, And but the peloton is going to catch the breakaway eventually if you've got no time limit on the race. And I think that's what happened in solar. Everyone, doing the same thing has been a real cost factor in getting the costs to where we see them now. So it's a shame to see all this bickering about patents that, in most cases are fairly trivial, the issues that are being fought over.
And Ivona, in terms of Perovskite and Perovskite tandems, you said that there's a real race on at the moment. Are you seeing, collaboration, or are we seeing a lot of secrecy and IP amongst the companies and developers?
Well, of course, both. I mean, for example, I gave how we are collaborating with machine manufacturers and with a silicon company or like PV company. But you also have, other research institutes and other companies that are forming other collaborations. But I think in a way, the beauty of science is also that you have a little bit of this competition, because yes, we are publishing and then you are learning from this. And then, you have kind of stack on knowledge throughout this process, because I think if it's only like one company or one institute working, it's kind of like you're preaching to yourself, so I do like this competition a little bit, because I think overall in the end it has a certain benefit, like both for the research community and the industry, but it needs to be done, I think, also with a certain scientific integrity. It needs to be done in a fair way, and it needs to be done in such a way that there is even, let's say, a fair playing field, right? So we shouldn't on purpose sabotage someone else's research or something like that. So competition is good as long as it's fair and let's say, healthy. Let's put it that way, yes.
And the teams of researchers all around the world, the peloton, will continue to drive solar technology and energy storage and integration forward. Thank you very much for joining me here today on the Smarter E podcast. Powering Through is the name of the podcast. I'm Jonathan Gifford, your host. Thank you very much, Martin Green, Nina Munska, and Ivona Kafadiska. Thank you for joining me, and thank you for watching.